So welcome to this new session. Now we have Bernhard Reinke from Aix-Marseille University who will talk about the Weierstrass root finder is not generally convergent.
Thank you, Jody, for the introduction, and thanks for the organizers for the opportunity to speak here. So today I want to present the result that the Weierstrass root finder is not generally convergent, and more generally I want to talk some new results about dynamics of high-dimensional root finding methods. And as a small introduction, as a motivation for root finding methods, you probably are all familiar with the joke that it's not the fundamental theorem of algebra, but the fundamental theorem for algebra, that every polynomial of degree d has exactly d roots. If you want to count this with multiplicity, this is classically attributed to Gauss, and most of the proofs are done by various methods, and for example, coming from also complex analysis, and this is why we like to call it for algebra and not of algebra. But you also are probably familiar with the result by Ruffini and Abe that if you go to degrees as least 5, it's not possible to find the roots just by doing finite many radicals and simple algebraic operations. So at some point you have to use iterative methods. And the Newton method was already discussed in Dirk's and also in Sergei's talk, and I won't say much about it, but it's a one-dimensional dynamical system where you iterate on one approximation, and the approximations try to find a single root. But there are also higher dimensional root finding methods, such as the Weierstrass method in numerical circles, more commonly known as the Durand-Kerner method, and the Ehrlich-Aberth method. And these are methods that try to find all d roots at the same time. And I want to talk in particular about the dynamics of the Weierstrass method, and if there's time, also about the some dynamics of the Ehrlich-Aberth method. And what kinds of results I want to present today are the following. So here's a small table, and we will fill this in during the talk. Namely that the Weierstrass method has attracting cycles, but it's not generally convergent. And the Weierstrass method, and also some variant, and also the Ehrlich-Aberth method, exhibit a new phenomenon which is different from the Newton method, which are diverging orbits going towards infinity. So what I want to do today is first to introduce the Weierstrass method and the Ehrlich-Aberth method. Then I want to say how you can find attracting cycles for the Weierstrass method, and then how you can also find diverging orbits to infinity for the Weierstrass method, and if there's time, also for the other two methods as well. So I already said that the Weierstrass method and the Ehrlich-Aberth method are high-dimensional root finding methods which try to find all roots of a polynomial at the same time. So if we have the space of monic polynomials of degree d, and I will call this in the future Ph.D, and we have a polynomial in this space, and we have some approximation vector z, and here are the coordinates of that approximation vector, then I want to find a better approximation vector for this. And the way I'm doing this is I consider the rational function, which is the polynomial divided by the monic polynomial, which has as roots all the other coordinates of my approximation. So Qi is P of z divided over the product where here I'm taking the product running over all j not equal to I of z minus zj. And the reason why I'm doing this is the following. If I already know the factorization of my polynomial and all the other roots are close to the approximation vectors coordinates zj, then the resulting rational function will be close to the linear function z minus the missing root. So if you take equal signs here, then this is a true statement. And as a heuristic, I'm replacing the equal signs with close by. And then you can explain the Weierstrass method and also the Ehrlich-Aberth method via these helping functions Qi. So what the Weierstrass method is doing is now trying to solve this Qi as a linear polynomial. So what you're doing is you take Zi and send this to Zi minus Qi of Zi. So this solves Qi as a linear polynomial. And what the Ehrlich-Aberth method is doing is applying a Newton step for this helper function Qi. And all of this happens for all coordinates at the same time. And so first I want to say something about the results for the Weierstrass method. Maybe we have the following, and I should mention that this is based on joint work with Dirk Schleicher and Michael Stoll. Namely, we have the following. There's an open set of polynomials for every degree, at least 3, such that the Weierstrass iteration method has an attracting cycle of period 4. And period 4 is indeed minimal with this property, in the sense that at least for degree 3, it is minimal. For higher degrees, we unfortunately don't know. But what we learn from this is that similarly to the Newton's method, the Weierstrass method is also not generally convergent. And while this was already conjectured by Smale, so far it hasn't been observed in practice. So this is a result which surprised quite a few people in the numerical community. And how did we manage to do this? So we tried to approach this from an algebraic perspective. And what we were considering is the following set of varieties. So we consider the following varieties. We take a polynomial, a monopolynomial of degree d, and we take a point which is periodic for the Weierstrass method of period n. And we look at the collection of all of this, and we call this Q d of n. And similarly, what we are doing is we are not only considering a polynomial and a periodic point, but a polynomial, a periodic point, and a linearization of the first return map. And we call this md of n. And you can realize these as algebraic varieties over the space of monic polynomials. And we know from classical dynamics that a cycle is attracting if all of the eigenvalues of the first return map are less than 1. So there's an attracting cycles of period n if and only if the projection of this space onto the set of multipliers intersects with the unit polydisk. And what we are trying to do is we want to try to find explicit equations for this variety, dm of md of n, and in particular we want to see what the equations for the image is. And so if we take the Zariski closure, then we can actually compute this with computer algebra. And then we want to check for intersections with the unit polydisk. How does this look in practice? We make first a few remarks about dimensions. So the dimension of this space, at least we expect it to be the same of the dimension of the space of monic polynomials. So we have dimension d for monic polynomials of degree d, but we know that multipliers are invariant under affine conjugation, and the Weierstrass method behaves well under affine conjugation. So if we then project down to the set of possible multipliers, we at least here lose codimension 2. So we can only expect something of codimension 2 in C to the D. But the variant of the Weierstrass method that we are considering has a nice property that Dirk already mentioned, namely that the dynamics is restricting after one step to a d-1 dimensional hyperplane of C to the D, namely to the hyperplane where the sum of coordinates is equal to the sum of roots. So one of the eigenvalues is always 0. And a further restriction that we can make is first deal with cubic polynomials and try to generalize from cubic polynomials from that case. And then the set of possible multipliers is given by a collection of curves in C2. And each of them can be given by a single equation. And we can try to compute these simple equations. And using these dimension counts, it becomes feasible for the Weierstrass method. How does this look for small periods? If you, for example, take general 2 cycles where you exclude some simple cases where one of the coordinates might be equal to the roots or something like this, then we have the following relation of the multipliers. Their product minus twice their sum plus 6 is equal to 0. And from this, you can easily see that the 2 cycles, at least the general ones, cannot be attracting, because otherwise, if they were attracting, then this product would have to be of modulus less than 1. And similarly, this sum has to be of modulus less than 2. So you cannot be something which gets to 0 if you add this up with 6. And similarly for period 3, if you take cycles of a special form, namely the one where you have rotation symmetry, namely after one step, you go to, if you start with Z1, Z2, Z3 to Z2, Z3, Z1, then this is, for the Weierstrass method, a 3 cycle up to symmetry. It's a fixed point, and it's easier to compute things like this. And then we can actually give a parameterization for the set of possible multipliers. And actually, we are using this symmetric property to describe the set of possible multipliers as third powers of 2 numbers which sum up to -3. And from this, it's easy to see that in those cases, cycles cannot be attracting. But if you want to go a little bit further, it becomes computational much more complicated. So here is the description of possible multiplier relations for general 3 cycles. And what we are doing here is we actually implicitly describing the set of possible polynomials that have as roots those 2 multipliers. And you can give a rational parameterization, and here's a nice complicated formula for this. And from this rational parameterization, we can also conclude that no 3 cycles can be attracting. And for this, we had to use a lot of computer algebra, and it seemed for a while that we couldn't go higher than 3 cycles for the Weierstrass method. But what we can do is actually go one step further by again using some symmetry argument. So what is possible is to look at 4 cycles where after 2 steps you are back to the original point up to symmetry, meaning after 2 steps, you have the original point, but you swapped the first 2 coordinates. And then this is again something which can be simpler described. And here again, we give now a relation of the coefficients of the polynomial that has its roots, the possible multipliers, and here it is. And from this, we can see that it's actually possible that there's a polynomial which has as a double root minus 0.689 something something. And in particular, this is of modulus less than 1. And from this, we can see that it's actually possible that attracting cycles arise. How does this look like? So here we take a real slice. If we take the polynomial z cubed plus z plus t, where can you see the bottom at the moment, or is this?
Well, there's something shown for your orientation.
Okay.
Now it's better.
So sorry about this. Yeah, we are taking a real slice, so we have a polynomial of the form z cubed plus z plus t, where t is close to 177. And in this case, there is actually a real orbit that is attracting, and then we can restrict ourselves to R3 sitting in C3, and the real hyperplane, so just a plane sitting in R3, which is given that sums up to 0. So we can use the parameterization for the first coordinate and the second coordinate, and then we set the third coordinate to be minus the first plus the second. And here you can then see the slice of the attracting basin of this attracting cycle, and you can already see from the scales that it is actually a relatively small set for some sense of measure. But I can also show you some picture from the dynamical, from the parameter plane. So here, again, we use the similar parameterization as before. We're using z cubed plus z plus t, and now t is our parameter. And we have 2 components here. And this is the blue component is a component with attracting cycles where we have this transposition symmetry, and the red the green component is a component where we have an attracting cycle which does not have this symmetry. On the real line, what's happening is that the real attracting orbit becomes complex, but then has some kind of twisted symmetry. After 2 steps, you get something which is transposed, which is complex conjugated to the original one. And I can also show you some pictures comparing this to the Newton parameter space. So this is now the classical parameterization of the Newton space. And when you zoom in here, then when you zoom in here again, you can see multiple copies. So we have multiple copies because we have different kinds of parameterization. So we already worked out a little bit the symmetry. And if you want to find the Mandelbrot set, you can also find this by zooming here and here. But this is also something that Dirk has talked a little bit more in detail. So this was the way how to find the attracting cycles. So we used computer experiments based on the variety of cycles and try to find parameters for which they are attracting. So now I want to briefly talk about the different phenomenon and at least say something about this for the Weierstrass method, namely diverging orbits of to infinity. And I will do this by first considering the simples cubic polynomial, namely the polynomial z cubed. And so I already mentioned that the Weierstrass method projects after one step to the hyperplane where the sums of coordinates is equal to the sums of roots. So here for this polynomial, it's just the hyperplane z1 plus z2 plus z3 is equal to 0. But from the affine symmetry from the Weierstrass method and the fact that 0 is fixed up to scaling, we see that the Weierstrass method for z cubed has an additional property, namely that it's homogeneous. And so we can then use this homogeneity to obtain a rational map on the space of lines going through 0 of this hyperplane, so the projective space associated to the vector space H. And we can do this in explicit formulas, as you can see here. And then the resulting rational maps that we obtained is a Blaschke product. It's conjugated to a Blaschke product, and its Julia set is the real line. And it additionally has I think in this coordinate, it has one fixed point in the upper half plane, one fixed point in the lower half plane. And from this parameterization, you can easily see that if you start with a vector where the triangle spanned by z1, z2, and z3 is not degenerate, so they are not on a real line, then this means that they have to converge to 0, 0, 0. But what is in particular interesting for us are the periodic points of phi on the real line. And we can use this in the following way. So we had this homogeneous property for the map z cubed, and we can use this to get a compactification of the Weierstrass method by looking at the now projective plane which has the hyperplane embedded as an affine plane. So before that, we were looking at lines on the hyperplane, and now we are basically looking at the projective plane which has as line at infinity lines of the original hyperplane H. And we can extend our Weierstrass method to this hyperplane, and this is more or less standard, that now the map at the line at infinity is given by our rational function phi. And now there is a periodic point on this line, which is repelling at the line in infinity, but has an attracting eigenspace direction, which is transversal to the line infinity. And then you can use the stable manifold associated to this periodic point to get diverging orbits. So we have for polynomials of degree 3 orbits that diverge to infinity, and you can easily promote this to every polynomial of degree at least 3 that has distinct roots by doing some kind of embedding and construction where you add as extra coordinates extra roots of the polynomial, and you will use distinct roots to make sure that everything is well defined. So how much time?
2 more minutes if you want.
Then I want to briefly also talk about the Ehrlich-Aberth method. So here's the formula for the Ehrlich-Aberth method and an equivalent formula where you see from this formula that the Ehrlich-Aberth method respects Möbius transformation. I think this is also called the electrostatic interpretation, and both Dirk and Sergey already talked about this. And so the fact that the Ehrlich-Aberth method respects Möbius transformations particularly implies that the natural way to compactify the Ehrlich-Aberth method is to look this as a rational map on P1 to the D. So we have a rational map P1 to the D to P1 to the D. And then this extension is then also, of course, symmetric with respect to Möbius transformations. And we can also get diverging orbits for the Ehrlich-Aberth method by finding a cycle with an attracting direction and move it around such that after Möbius via Möbius transformations, such that one of the coordinates of the cycle becomes infinity. And there's a nice geometric construction for this using the notion of harmonic 4 tuples, but I probably won't say too much about this. So here's again the table I mentioned at the beginning, and so we have seen the attracting cycles for the Weierstrass method and the diverging orbits for the Weierstrass method, and a sketch of the diverging orbits for the Ehrlich-Aberth method. There's also a variant, which is the Gauss-Seidel variant of the Weierstrass method, that also has diverging orbits. But the crucial point here is that we don't have this restriction to a hyperplane anymore. So this is actually a dynamic system of dimension D. Yeah, I think this is a good place to stop this discussion here. And if there are questions concerning the table, I can